In recent years, there were many major breakthroughs in artificial intelligence and machine learning, including successful applications in medicine, logistics, and intelligent productions. Nevertheless, even experts require weeks or even months to develop new successful machine learning applications. Besides defining the task and collecting new data, designing the machine learning pipeline is a tedious, error-prone, and time-consuming task. However, it is essential to achieve top performance. By automating the machine learning design, we support developers by reducing the required expert knowledge and by enabling an efficient development of new machine learning applications. We call this automated machine learning.
The algorithms we have right now work decently. Still, to make them more performant, time-efficient and robust, we need to appropriately set their hyperparameters. As of yet, we set them statically. However, for iterative algorithms, there's evidence that using dynamically adjusting hyperparameters is more beneficial to navigate the optimization landscape. Therefore, we are working on finding dynamic hyperparameter schedules automatically in a data-driven way.
In reinforcement learning, we want to solve a broad range of tasks. A robotic arm, for example, is supposed to be able to pick up objects of all shapes, boxes or cylinders, for example, from all directions it can reach without having to train individually in each of these subtasks. However, as we want to stay efficient, both in terms of time but also computational cost, we need to train smarter instead of just using more data. Meta-learning is a way of discovering these smart training methods in order to transfer one solution from a problem domain to another, for reaching new performance heights through, for example, better exploration or task orderings, and to robustify the agent against changes in its environment.
Training machine learning models requires tons of magic numbers and are essential for their performance. However, finding this optimal configuration requires human expert knowledge and lots of trial and errors. And Bayesian optimization is one of the most prominent approaches for doing hyperparameter optimization that emphasizes trading of exploration, that is, looking for good configuration, and exploitation, that is, searching for better configurations. And that is what I'm currently working towards, automating the design choice of a machine learning pipeline to support the developers and speeding up the development of new machine learning applications.
Many interesting problems, rich relations can naturally be cast in form of a graph, either immediately, as with logistics or proteins, or after pre-processing, in the case of texts and images, all of which allow for complex reasoning. Graph neural networks are a capable means of analyzing this complex structured data and generating insight from it. Due to the data structure's expressiveness, these networks can be brittle. My task is to leverage statistical evidence to guide experts' intricate design decisions regarding the architecture and hyperparameters.
So far, we have heard how important hyperparameter optimization is. But even by today, it's not as much used as it should be. To make AutoML more transparent, trustworthy, and also attractive for everyone, we aim for automatic explanations of the process. There are already some approaches like hyperparameter importance or performance over time, which create the first level of trust of automatic hyperparameter optimization. But to further increase the trust, I'm designing a framework which is both compact and easy to use.